Okay, in this final part of the introductory overview, I want to talk about equational reasoning. So we've previously defined a number of Haskell functions by means of pattern matching, and I hinted at the fact that in order to reason about the evaluation of a Haskell program, it's good to understand how to systematically go about it. And this is really not difficult. The idea is just that if you start with an expression, that you look at what is the outermost function application in that expression, you find the definition of the corresponding function, you perform pattern matching in your mind properly, right? You find the corresponding equation that matches, you replace left-hand sides by right-hand sides, and you repeat until no more reduction is possible. Right? That is what is being called equational reasoning. So let's look at a concrete example in terms of the elem function. So let's once more look at our elem function that we had been defining. So elem was of type EQA, double arrow A to list of A to bool, right? And we had two cases. If we look for anything in the empty list, then it is false. If we look for anything in a non-empty list of shape y cons ys, then we check whether x is equal to y or whether x is an element of ys. All right. So now, if we have a call such as this one, elem 9 of the list 6, 9, 42, okay? Now I've given the two functions that primarily play a role here, I've given their definitions once again down here without the type signatures because they don't really play a role for the reduction. We only have the equation so that we can look at the pattern matching. And the goal is to evaluate this step by step to get an idea of like how we can think of the semantics of a Haskell program. So first thing to keep in mind is that this convenient list syntax is actually just convenience. It's a so-called syntactic sugar. It's a shallow layer of syntactic convenience that hides the internal representation that is actually the truth. So really, this is more correctly expressed as that. So we have a call of elem 9 to the list 6 cons, 9 cons 42 cons the empty list. I've given the parentheses here, even though they can be omitted, just to make it entirely clear what the structure of this function application here is. Now, if we look at this expression now, after having removed the syntactic sugar, it's an application to the elem function, right? So at this point, we start looking at the definition of the elem function, and we start checking whether this call, this concrete call we have here, whether that matches the first or the second equation, the second case. It does not match the first case because here we expect an empty list, but we have a list that is 6 cons something. All right. The second case matches because we expect y cons ys and we have 6 cons something. So now we have found a case that is matching. Now we replace this left-hand side with this right-hand side while maintaining, right, the local assignments between variables and expressions that have been created by the pattern match, right? So because the second left-hand side here matched, we now have that x is equal to 9 for this particular reduction, y is equal to 6, and ys here is equal to 9 cons 42 cons the empty list, right? And with these three assignments, we replace the left-hand side with the right-hand side. So we get 9 equals 6 because x is equal to 9 and y is equal to 6. Or elem x is 9, elem 9, and then ys is 9 cons 42 cons the empty list. So this is the next expression that we're getting. Now here we have to look at what's the outermost application in this expression. That is slightly harder to see, right? Because it's a more complicated expression. But really this is an application of OR, right? And the left argument of the OR is 9 == 6. And the right argument of OR is this recursive call to elem. Now we can look at the definition of OR. And now we see something interesting that happens occasionally, right? In order to make a decision between these two cases here, we have to know what the first argument of OR is. We have to know whether this is false or whether this is true. So we cannot, at this point, immediately make this decision. We have to evaluate the first argument further until we can make that decision. So now we would actually have to look at the definition of equals equals. Okay, and that's where I'm going to stop here, because this is ultimately going to boil down to something that is primitive, not in one step, but it essentially here comes down to a machine instruction that compares two integers for equality. So if we assume that this equality test is implemented sensibly, then we would expect that the result of 9 == 6 is false. So if we assume this, that 9 == 6 evaluates to false, then we get this expression. And now we can return to the question of reducing OR, right? Because now we do have that the left argument is of the shape false, and it actually matches the first equation, and then we get y to be equal to this recursive call, and that also becomes the result. So we get elem 9 cons 42 cons the empty list. Okay, at this point we have another call to elem, but on a shorter list, right? And we are in a relatively similar situation to the beginning. So we look at the definition of elem again. Again, the first case does not match because the list is not yet empty, right? The second case does match. X is still 9, but y is now also 9, and ys is 42 cons the empty list. Okay? And then we replace the left-hand side with the right-hand side again, and we get this. And now we have a call to OR again, and we are again in the situation that in order to make a decision between the two cases for OR, we have to know what 9 == 9 evaluates to. But if 9 == 9 is sensibly implemented, it should evaluate to true, so we will get this. And then we see that now not the first case of OR matches, but the second case of OR matches, with y being elem 9 42 cons the empty list. Okay, but now we replace the left-hand side with the right-hand side, and the right-hand side is just true, and that is our final result. Okay, and indeed, if we go into our GHCi window and we make the same call, right, elem 9 6 cons 9 42, we also get true. Now, Haskell is a compiled and potentially strongly optimized language. What actually happens in the compiled code is not directly corresponding to what I've just shown, right? So there are possibly many shortcuts being taken, and many things are handled in a slightly different manner. But as a conceptual model to predict the right result, this equational reasoning is exactly the right thing. Whatever the compiler does, it should lead to the same result. Okay? So this is fine. This equational reasoning is a fine method to convince yourself that a certain expression reduces to a certain result. Equational reasoning can be used also to reason about certain programs being equivalent, whether you ask yourself, is it safe to replace this program fragment with another program fragment? You can apply equational reasoning. Equational reasoning can even be applied in an automatic way by the compiler to perform certain optimizations and refactorings. So this is a good model to keep in your mind. And actually is one of the strong points of functional programming, that this is feasible even in large programs up to an extent, because things are very local. You typically have function calls where all the inputs are explicit. There is no global state to take into account. There are no sort of strange interactions with other stuff. You basically have all out in the open, and at least sort of on a small scale in a large program, equational reasoning can be employed quite successfully. And I'm using it as a reasoning principle while developing Haskell code nearly all the time without even thinking too much about it. Okay. There is one more thing that we have basically implicitly using here, but is actually quite impactful, and that is that we have made a choice how we have defined OR, and that choice actually played a role for how we perform the equational reasoning in our elem call before. Because let's have a look at the end here again. Here we have a call true or elem 942 cons the empty list, and we reduced that in one step to true. And this was possible because we have a definition that says true or anything is true. So note in particular that we never actually evaluated this recursive call. Right? So we did not reduce this any further. elem 942 cons the empty list. If we started reducing that by equational reasoning, we would ultimately get false. But we didn't actually do this because we already had this case and we immediately deliver true. And that is mirrored by what Haskell internally does as well. Haskell employs so-called lazy evaluation strategy. And that is exactly this idea that we are always looking at the outermost call. So in this case, we have a call to OR. And we are making a reduction as soon as possible. So only because OR actually needs its left argument in order to decide between the two cases, we started evaluating the left argument. But then we didn't evaluate the right argument because we could make the decision without looking at the right argument. And we only, sometimes we will subsequently look at that argument, like in this reduction of OR where we had false, we then return the second argument and then we still end up reducing it. But in this particular case, for example, we completely discard it. Okay. And this notion of only looking at function arguments and only evaluating them when they're actually needed, this is exactly what is referred to as lazy evaluation. And it depends on how you define OR in this case, right? This is just one example of where it plays a role, but it depends on how you define OR. Had we defined OR with the for case distinction that I've briefly mentioned, where we make all four cases explicit, then in order to reduce OR, we actually need to know what both arguments are, and then this wouldn't be possible. And this is actually observable. We can observe that Haskell actually behaves this way. And I can do this by showing you in GHCi. So first of all, we have seen before the function enum from 2, right, which creates a list. Because I want to create a large list now, I'm going to refer to that. And actually, there is a shorthand notation, another syntactic peculiarity of lists, that allows us to write 1.100, and this will refer to the same thing. I mean, if I write 1.100, it means exactly the same thing as calling the enum from 2 function from 1 to 100. It's just a more convenient syntax for it. And I can go even further. I can make a really large list now. Okay? So something that if I look for, let's say, 0 in this list, I will actually have to wait for quite a while. before I get the answer false, because this is already a really long list that has to be traversed. And the interpreter is slower. If I compile this and optimize this, it would be faster. But still, I mean, after a certain length, it will take a while to traverse it. But if I call this with 2, let's say, which is relatively at the beginning of the list and is actually in the list, I'll get true almost immediately, right, without any delay. Whereas if I'm looking for something that is not contained in the list, I have to wait for quite a while. And this shows us that this lazy evaluation is actually happening, right? Because this is exactly because after just a few reduction steps, I hit the case where, in this situation, where I'm comparing 2 with the first element of the list, and I can jump out of this OR definition without ever reducing the second argument to OR, right? And I can show further that if I had been using a different definition for OR, right, the one that we have been discussing as well, with all 4 cases, that this would no longer work. So now if I reload and I do this, now I have to wait a long time for the result of elem 2 in this list as well. Okay. In many other languages, actually, this is even worse for other reasons. So here we get an actual Stack Overflow, and we'll come back to these kinds of performance problems at a later point, when they arise and how they arise. So so fortunately, we don't have this, right? Because we have this version of OR, right? Another thing that this means, though, is that it's also important in which order I'm calling OR here. I mean, if I make the recursive call first and then compare the first elements, then my definition of OR is not compatible with the shortcut behavior that I've implemented here. Right now, I have to make the recursive call in any case, because the first argument of OR is needed in order to make progress. So this is going to behave badly as well, even though it has the good definition of OR. Okay, so let's interrupt this. So you have to do things correctly. So that is a little bit subtle. At the same time, it's also very nice, though, because it really just follows from the general principles, the general evaluation principle. Many other programming languages actually have special behavior for these kinds of logical operators, because it's often quite desirable for AND and OR to have this shortcut behavior. If you know that the first argument of an AND is false, you can immediately say false. If you know that the first argument of an OR is true, you can immediately say true. Many other programming languages actually have special built-in shortcutting behavior just for these logical operators. For Haskell, you don't need this. For Haskell, it just follows from the general principle, and you get similar kind of shortcutting behavior in lots of other situations. Another cute example is that there is a function enum_from that is not enum_from2 that starts enumerating numbers from 1 but never stops. So it produces actually an infinitely long list, which I have to interrupt here at some point. And I can do the same thing as 1 ... which also produces a potentially infinite list. But it's fine to print it and to evaluate it as we go, right? This works also due to lazy evaluation. And it's also fine to say use the take function on such a potentially infinite list and only evaluate a finite prefix of it. And all the rest from 11 onwards will never be evaluated. And there's no problem that we have a computation that would never terminate because we're not using it anymore. And we ultimately look at a finite prefix. And often this allows us to structure programs in a nicer and more compositional way because we can separate different concerns. We don't have to worry about like putting bounds everywhere, because we can do so separately at a later stage due to lazy evaluation. Okay, so the general tagline here is that we only evaluate things once they are actually needed. Okay. So this brings us to the end. Let's recap once more. So at the beginning of the introduction, we have been looking at expressions, and then we have been looking at types for quite a bit, and then we have been looking at bindings. But now in this final part, we have really been looking at pattern matching and defining new data types, defining functions on new data types or existing data types using pattern matching is probably the most fundamental part of Haskell programming, right? This notion of distinguishing multiple cases, one per data constructor, and following the shape of the underlying data type, also in the sense that we recurse when the data type is recursive, such as lists are. That's really what I think the essence of fundamental beginning Haskell programming. And we will do this again and much more in the upcoming videos, right? Also note that it is very easy to define new data types, and defining data types is an integral part of writing Haskell code. When you start developing a new system, you typically in Haskell you start by defining domain-specific data types that capture the concepts that you want to express. That's really at the core of it, and then you start giving them operations. And new data types start out with no operations except pattern matching. The only thing you can do if you're not using some deriving magic is to define functions by means of pattern matching. So it is really the most fundamental thing you can do. Okay, thank you for listening.